Welcome to the deep dive, where we kind of roll up our sleeves and dig into a topic you want to learn more about. Today, it's something that's been making waves, quantum computing, and more specifically, we're looking at something that's been holding it back.
Yeah, a big challenge.
Yeah, you could call it a speed bump on the quantum highway, and it's this thing called decoherence. It's a mouthful, I know,
It is.
but it's crucial to understanding where we are with quantum computing today.
Yeah.
So to help us break it all down, we've got an expert on board.
Glad to be here.
So let's just start with the basics. What is decoherence site? Can you break it down for us?
Well, you can think of it like this. You have this quantum computer, and it's using these really special quantum properties like superposition and entanglement.
Right,
And it's using those to do these incredible calculations that you just can't do with a regular computer.
right. Amazing potential.
Yeah, but there's a catch. These quantum states that we're talking about, they're incredibly fragile. Like, think of a delicate snowflake.
What?
And decoherence site is basically the amount of time that a quantum system can hold on to these properties before the outside world causes it to decohere.
It's you to hear.
Yeah, or to lose its quantumness, I guess is another way of putting it.
So it sort of collapses back into being just a normal system.
Exactly. It can't do those quantum calculations anymore. And this is exactly what Yargo Schneppat talks about in his writing, too.
So it's kind of like a ticking clock then for quantum calculations. Like the longer the decoherence site, the more complex the calculations you can perform.
Yeah, exactly. If you have a short decoherence site, it really limits the potential of quantum computers. It's like trying to write a whole symphony, but the paper keeps bursting into flames after you write a few notes.
That's a yeah, pretty vivid image. So what is it that actually causes this decoherence thing? Why are these quantum states so sensitive to the outside world?
It's all about interaction with the environment. Even the tiniest disturbance, like a stray photon, a particle of light,
Uh,
or even just a small change in temperature. Yeah, anything like that can mess up the balance of a quantum system. Imagine trying to balance a spinning top on a surface that's constantly vibrating.
right. Yeah. Wouldn't go so well.
Exactly. It's a tough job, and it's something that Schneppat really emphasizes as well.
So it's not just about building these quantum computers. It's also about shielding them from all of this environmental noise.
That's right. And you know what makes it even harder is that as quantum systems get more complex with more qubits, they become even more sensitive to all these disturbances.
Right. More things to go wrong.
Hmm.
So this makes me think about the different types of quantum computer architectures. Are some of them just naturally better at resisting this decoherence than others?
Yeah, that's a great question, and it's something researchers are really grappling with. You see, there are trade-offs. So, for example, you have superconducting qubits, which are pretty easy to make and control.
Okay.
But unfortunately, they have these shorter decoherence siten and are super susceptible to any electromagnetic interference.
Oh, so it's like a trade-off ease of use versus the amount of time you have to actually work with it.
There are always trade-offs. Then you have something like trapped ion systems,
Okay.
which are much harder to engineer,
Right, yeah, yeah.
but they use these trapped ions in a vacuum.
Uh-huh.
And that means they can stay coherent for much longer.
So if superconducting qubits are like that symphony on burning paper,
Mm-hmm.
are trapped ions the more durable parchment?
You got it. It's a good way to think about it. And it just shows you the challenge for these researchers finding the right balance between how controllable they are, how scalable they are, and of course, how long that coherence time is.
Yeah, that's a tough job.
Yeah, it's a balancing act for sure, and one that researchers are really tackling from all sides.
So let's get into that.
Hmm.
What are some of the things scientists are doing to fight this decoherence problem?
One way is to go to extremes with how much they control the environment.
Extremes? How so?
I'm talking ultra low temperatures, like barely a fraction of a degree above absolute zero. That's to cut down on all those thermal vibrations. And they're also using special materials and shielding techniques to block out all those stray electromagnetic fields and other interference.
So it's like they're building fortresses for these quantum computers?
Pretty much, but it's not just about physical isolation.
Yeah.
They're also working on these really sophisticated error correction algorithms.
What do they do?
Well, think of them as like mathematical guardians. They can detect and correct those errors that pop up because of decoherence.
So they're trying to outsmart the environment,
Yeah.
basically compensate for all the disruptions.
Yeah, exactly. And There's a lot of research happening in this area with lots of different approaches, and one of them is this thing called dynamical decoupling.
Dynamical decoupling.
It uses these carefully timed pulses to average out the noise from the environment.
That sounds super complicated.
It is, but it's showing a lot of promise. And then there's research into quantum error correction guns.
What are those?
They're designed to encode the quantum information in a way that makes it more resistant to errors.
So it's both hardware and software solutions working together.
Absolutely. It takes expertise from all these different fields: physics, engineering, computer science, even math.
This reminds me of something Schneepat wrote in his essay about how this whole pursuit of extending decoherence sight is really pushing innovation in material science and engineering.
Yeah, he's totally right. The need for longer coherence times is leading to the development of all these new materials with amazing properties.
What kind of properties?
I'm talking about materials that are more stable, less susceptible to noise, and just better suited for quantum applications.
So it's not just about making better quantum computers, it's about pushing the boundaries of material science as a whole.
Exactly. And these advances could have huge impacts beyond just quantum computing. They could revolutionize things like energy storage, electronics, even medicine.
It's pretty wild to think that this challenge, this decoherence sight, could actually be a catalyst for so much innovation.
It's a great example of how fundamental research can lead to breakthroughs in all sorts of unexpected areas.
It really makes you wonder what other scientific challenges are out there holding back even greater discoveries and what those discoveries might unlock.
Absolutely. And it's that sense of wonder and possibility that makes the field of quantum computing so exciting.
Now that we've kind of gotten a handle on the enemy, so to speak, let's look at the battleground. What are some of those exciting applications that are waiting for us on the other side of this quantum speed bump?
One area that's getting a lot of buzz is drug discovery and material science. Quantum computers could totally revolutionize the way we design new drugs and materials because they can simulate molecular interactions with crazy accuracy.
So instead of spending years and millions of dollars in a lab, we could test virtual prototypes on a quantum computer and figure out which ones are the most promising.
That's the idea. It could speed up the process a ton and lead to the development of life-saving drugs and totally new materials.
That's amazing. What about other fields?
Finance is another area where quantum computing could have a huge impact. Quantum algorithms could optimize investment portfolios, assess risk way more accurately, and create whole new financial instruments.
So Wall Street might soon be full of quantum analysts.
Yeah.
What about cryptography? I know there's a lot of talk about quantum computers breaking our current encryption methods.
That's right. Quantum computers are a real threat to the encryption algorithms we use today, which rely on how hard it is to factor really big numbers.
Oh.
But the cool thing is that those same quantum principles that threaten encryption can also be used to create unbreakable quantum encryption methods.
So it's a double-edged sword. They can break our codes, but they could also create new ones that are way more secure.
Exactly. It's like an arms race. And it really shows how important it is to stay ahead of the curve when it comes to this technology. Schneepat actually touches on this a bit in his essay.
This all sounds incredibly exciting, but also a little bit scary. It's clear that quantum computing could change the world in some pretty big ways. But it also brings up a lot of questions about ethics, security, and the future of society.
Absolutely. As we go deeper into the quantum realm, we really need to have some thoughtful conversations about what this technology means for society as a whole.
It's a good reminder that scientific progress isn't just about pushing the limits of what we know. It's also about understanding the consequences of those discoveries and making sure we use them responsibly for the good of everyone.
Well said.
It sounds like we're on the edge of this quantum revolution, but we've been talking about decoherence sight as this big roadblock. But even if we figure out how to make those coherence times longer, there's still this whole issue of scaling things up.
Right. That's huge.
Like-
You know, it's one thing to build a quantum computer with a few qubits in the lab. It's a whole different ball game to create systems with hundreds, thousands, maybe even millions of qubits.
Right, that's what we need for the applications we were talking about. So how do we get there? From these little prototypes to these large-scale, super powerful quantum computers of the future. What are some of the challenges when it comes to scaling these systems up?
One of the biggest is just keeping things coherent as the number of qubits grows.
Right.
The more qubits you have, the more complex all the interactions get, and the easier it is for decoherence to sneak in.
Yeah.
Schneepat makes a good point about this. It's
Yeah.
like trying to conduct an orchestra with millions of instruments, each one playing its own thing and super sensitive to the slightest disturbance.
Wow, that sounds impossible.
It's definitely tough, but there are a bunch of different approaches researchers are trying out. One is to use modular architectures, where you connect smaller quantum processors together to make bigger systems.
So instead of one giant quantum computer, you have a network of smaller ones.
Exactly. And the good thing about this modular setup is that it's more scalable and fault tolerant. If one module fails, the others can keep going.
That's a good backup plan.
Yeah, for sure. Another area that's showing promise is topological qubits.
Okay, I've heard that term thrown around.
Yeah.
What are topological qubits?
Well, they're this new type of qubit that are supposed to be way more resistant to decoherence, and that's because the way they encode the quantum information,
Hmm.
it's encoded in a topological property of the system.
A topological property? What does that even mean?
So think of it like this. Instead of storing information in the state of a single particle, like in regular qubits,
Okay,
topological qubits encode the information in the overall shape or structure of the system.
interesting.
And because these topological properties are so robust, they're much less bothered by that environmental noise we keep talking about.
That makes sense. So is this the magic bullet everyone's been waiting for?
Yeah.
What are the downsides?
Well, one big one is that the research is still really early days.
Oh, so it's not quite ready for prime time.
Not yet. Scientists are still figuring out how to create and control these exotic particles.
Yeah.
It's really cutting edge stuff.
It sounds like it. So it sounds like it's still a race to see what's going to be the best way to build these large-scale, really powerful quantum computers. Is there a clear winner so far?
I don't think so. It's such a fast-moving field. There are so many different teams working on this stuff. It's a really exciting time to be in quantum computing. Schneepat is definitely right about that.
It makes you wonder what the world's going to look like when we finally do have these large-scale, fault-tolerant quantum computers.
Yeah, it's hard to even imagine. We've talked about all these potential uses in medicine and materials, science and finance, even cryptography.
Uh-huh.
But who knows what other crazy applications we haven't even thought of yet.
Yeah, it's like we're on the edge of this whole new world.
It really is. And who knows what we'll find.
Well, this has been an incredible journey learning about all this with you. We've covered a lot of ground, the challenge of the coherent site, the ways scientists are tackling it, and all the incredible possibilities that are waiting for us in the quantum future.
It's been a pleasure talking about this with you.
And for everyone listening out there, just remember that while Decoherence site might be a bump in the road, it's also driving some pretty amazing innovation and discovery. So keep learning, keep exploring, and who knows, maybe you'll be the one to make the next big breakthrough. Thanks for joining us on The Deep Dive.